We're going to look at section 9.5b, mathematical induction and counterexamples. We'll talk about what those mean. And by the end of the lesson, you should be able to use mathematical induction to prove mathematical statements. And you can also use counterexamples to disprove mathematical statements. And we'll take a look at some examples of both. But what is proof by mathematical induction? It's a three-step process to prove that a statement is true for all natural numbers n, so counting numbers 1, 2, 3, 4, and so on. Step 1, the base case, show that the statement is true for n equals 1. Step 2, assume that the statement is true for some other natural number k, doesn't matter what the number is, and then prove that the statement is true then for the next natural number, k plus 1. And we'll look at the examples to show what that means. So, suppose I have this statement, 1 plus 4 plus ... plus 3n minus 2, so we don't know what n is, but it could be any natural number. We want to prove that that is equal to n times 3n minus 1 divided by 2. So how can we prove that this statement is true for all numbers n? Well, first thing we have to do is show that it's true for n equals 1. This is called the base case. And here, 1 times 3n minus 1 divided by 2 is equal to 2 divided by 2 is equal to 1. And yes, that is my first term. So when n is equal to 1, over here it's 1, and on this side of the equation it's 1. So the base case is true. Now, we're going to assume that the statement is true for some natural number k. And we're going to do that by just simply plugging in k anywhere we see an n. So 1 plus 4 plus ... all the way up to 3k minus 2 is equal to k times 3k minus 1 divided by 2. I'll give you a second to jot that down. Okay, now the next thing we're going to do is look at the k plus 1 term, okay? So we're going to substitute k plus 1 for k on both sides of the equation. Actually, we're going to add that to both sides of the equation. So add the k plus 1 term to each side. So if 3k minus 2 is my kth term, 3 times k plus 1 minus 2 is my k plus 1 term. Well, I have to add that same exact quantity to both sides of my equation. Okay, so I'm going to take my k plus 1 term. So that's going to be 3 times k plus 1 minus 2. I'm going to add it to both sides of the equation. Now, what am I going to do? I'm going to simplify. So I'm going to take this and find the common denominator. I'm going to multiply top and bottom of this by 2. So I have a common denominator of 2. And I'll give you a second to jot those notes down. Okay, now let's take a look when we combine like terms here. I'm going to multiply this side, this first term through by k, so I'm going to have 3k squared minus k, and I'm going to multiply 2 through on this term, so I'm going to have 6k plus 6 minus 2. So what does that look like? 3k squared minus k plus 6k plus 6 minus 4, because we had a 2 times 2. And that is all divided by 2. So combine like terms and simplify. I have 3k squared plus 5k plus 2 divided by 2. Well, I can factor the numerator into k plus 1 times 3k minus 2, all divided by 2. And now I'm going to play a little trick here. I'm going to take this 3k plus 1 and make it look like this so I can put it in the form that I want. So I'm going to take k plus 1 times 3 times k plus 1 minus 1 divided by 2. And this is the form that we're looking for because we wanted to prove this. So now my k plus 1 term is equal to k plus 1 times 3 times k plus 1 minus 1 all divided by 2. So I indeed did prove what I was setting out to do. So I'll give you a couple seconds to get those notes down. And if you need to go back and get those notes, you can do that. All right, let's look at another example. Use mathematical induction to prove that the sum of the first n odd numbers, 1 plus 3 plus 5 plus 7 plus dot dot dot, all the way up to some 2n minus 1 is equal to n squared. Well, what's that going to look like? First, I have to show that it's true for the first case. N is equal to 1. Well, my a sub 1 is 1. And n squared is 1, so 1 is equal to 1 squared. Well, that's pretty simple. Step 2, let's substitute k for some value n. And we have 1 plus 3 plus 5 all the way up to 2k minus 1 is equal to k squared. Now, what are we going to do for step 3? We're going to take the k plus 1 term. So I'm going to take 2 times k plus 1 minus 1, and I'm going to add it to both sides of the equation. So what does that look like? 1 plus 3 plus 5 plus dot 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 plus 2k minus 1 plus 2 times k plus 1 minus 1 is equal to k squared plus the same term. Okay? So I'm going to add this term to both sides. Now I'm going to work with the right side of the equation and see what I can get that to equal. So k squared plus 2k plus 2 minus 1 is equal to k squared plus 2k plus 1. I can factor that into k plus 1 times k plus 1, which is equal to k plus 1 squared. So we indeed proved that 1 plus 3 plus 5 all the way up to 2n minus 1 is equal to n squared because I proved it for the k plus 1 term. So I'll give you a couple seconds to jot those notes down. All right. So now let's look at counterexamples. We used induction to prove that a statement is true, and now we're going to use counterexamples to prove that a statement is false. Now, all we have to do is find one counterexample to make the entire statement false. Even if it's true for almost every number, if we can find one situation where it's wrong, then it is not a true statement. So use a counterexample to prove a cubed is greater than a squared, where a is a whole number. Well, if I look at 4 examples here, 3 cubed is definitely greater than 3 squared. 2 cubed is greater than 2 squared, but 1 cubed is not greater than 1 squared, and 0 cubed is not greater than 0 squared. So just because the first 2 are true, I found 2 counterexamples to make the whole thing not true. So a helpful hint here is, numbers like 1, 0, negative numbers, fractions. A lot of these sometimes can help us to find counterexamples. So again, all you need to do is find one counterexample. All right, let's take a look at an example here. Identify a counterexample to disprove a squared divided by 2 is less than or equal to 2a plus 1, where a is a real number. Well, let's assume that a is equal to negative 1. Is negative 1 squared, there should be a divided by 2 here, sorry. Is negative 1 squared divided by 2 less than or equal to 2 times negative 1 plus 1? No. 1/2 is greater than negative 1. So this statement is not true. Again, sorry, there should be a divided by 2 there. It should be negative. Should be a -1 squared divided by 2. All right, so here is our homework for today. And hopefully you are caught up with your Alex. Um, but take a look at the homework and make sure you get it turned in by next class along with the notes. So that's where we're going to finish for today.